Hi, I'm Paddy Delaney from Huber, and today I'd like to discuss PID tuning and more in particular true adaptive control. In our previous webinar and white paper, we've discussed the sizing of applications on TCUs and chiller units. In particular in this webinar, I would like to discuss chemical reactors and temperature control units and how to optimize your heating and cooling ramps now that we've already sized the unit correctly and purchased a Huber unit. Since the early 80s, Huber has worked with many chemical companies and with many providers of reactor technology, be it glass reactors, stainless steel, glass-lined stainless steel, and the latest variants of flow reactors and plug flow reactors, photoreactors. We work with the world leaders in these fields. And this can be seen in this slide here with all of our friends that we work with. And then working from our case study catalogue, we've learned how to tune reactors as well to get the optimum performance out of them. So if we look at our reactor systems, we've done the calculation on power. We know that we've got 3 different zones we've got to work with. We've got the total system weight, we've got the total thermal fluid weight, and we've got the reaction medium, all of which are critical. And all these components come together to how quickly or how slowly we can transfer that thermal energy from the temperature control unit to the application. And again, as in the previous webinar, we've discussed how thermal fluid can have a massive impact on this, using something with a high specific heat capacity or a low specific heat capacity. And you can look back at that presentation to read that further. So, what are PIDs and TACs and all these random terms that we come up with, acronyms? So, PID is essentially a control system used in industry to optimize your, in this case, temperature control or whatever the application is you're using. In the case of Huber, people will place the reactors generally in laboratories. That's no problem, we can handle that. But where do they put their temperature control units? Sometimes they're outside of a safe zone, sometimes they're underneath the fume cupboard, in a utilities corridor, plant room, or even in some cases up on the roof, because that's the only place they can fit them. Space is at a commodity in a lot of R&D and manufacturing sites. But a key factor here is, with regards to overshooting and undershooting, is the distance between the TCU and the application. When the TCU sends a packet of energy, how long does it take to reach the application? And will that cause your temperature control to overshoot or undershoot? So say that we have a set point here. We'll call this line X. And when heating up, due to the distance of the application from the TCU, at what point does the machine slow down? So you get a nice curve and you hit your set point perfectly. In the real world, this is very difficult to achieve without a bit of knowledge and a bit of practice. In most cases, what you see is you will heat up, you will overshoot. The unit will then counteract by applying cooling, it'll then counteract again, heat, cool, heat, and will eventually hit your set point. Or your unit will react too early and will perhaps never hit your set point. So we've got 3 options here. We've got A, we've got B, and we've got C. This is why we often need to tune applications so that we get the correct temperature control, so that we hit the set point and we hold the set point that people want. If we think of classic PIDs, these are kind of an on-off scenario. it kind of looks like A, where the unit is heating up, it turns off, it cools down, it turns back on, goes up and down, up and down, up and down. When choosing a temperature control unit, if you look at the tech data sheets, you will often see stabilities quoted. If you go for essentially a classic PID controlled system, you will see that your stability will be plus or minus, on average, between 1 degree and 5 degrees, depending on the size of the unit. The bigger, the more kilowatts you have, is probably more erring on the 5 degrees C. If you look at the Huber Tech data sheets, if we take, for example, the Unistat, which is our closed hydraulic system that we talked about in the last webinar, we're at plus or minus 0.01 degree. Or if we looked at our open bats, such as our Ministat, our stability is plus or minus 0.02 degrees. And in this will lead you to think, I can get tighter control and we won't get as much overshoot or undershooting. How do Huber do this? So, as mentioned before, we've worked with many chemical companies, many technology manufacturers for applications used in industry. And to get around this, we come up with true adaptive control. But to understand true adaptive control, we're just going to have to take a wee look at what are PIDs and what are the various methods within our Huber unit of setting our TAC values. So the easiest way of thinking about PIDs is if you think of a car driving up a hill. In the first instance, we're going up a hill. This would be our proportional value. And we're trying to go up a hill. If we set cruise control to 75 kilometers an hour, we're going up a hill, the car will slowly accelerate to go up the hill. And once it hits 75 kilometers per hour, it stops in a whole 75 kilometers per hour. But this is only true if we're going along a flat surface, because we can get the temperature, there's no resistance going against the application. Whereas in a chemical reactor, you've got your full thermal load of your reaction media and what's going on in the pot, basically. So that's our proportional term. If we look at our I, our integral term, this follows on from our proportional, where we've reached our 75 kilometers per hour, but we'd like to just increase our speed a little bit. So in this case, we do a minor adjustment. We check where our status quo, we do a minor adjustment, and we'd increase our speed slightly. But again, this only really holds true if we're on a kind of a flat trajectory and we've got no opposing forces from our thermal load. And our final is our D derivative, where this is truly where we're actually going up a hill from a flat. So we'd have to set our cruise control, get up to 75, 80 kilometers an hour. And then we've got to look at the road ahead. Is there potholes? Is there a bend? Or in the case of a chemical reaction, are we expecting an exotherm? Are we expecting a precipitate, a crystal to fall out? And in this case, if we look at the car analogy, we'd check our speedo, we'd adjust our speed control, but for the D term, we adjust to road conditions. So it might mean accelerating a wee bit, decelerating a wee bit, and all this you'd see adjusting in the proportional band. So on a Huber unit with a Pilot 1, you can go into the menu and you can select, do I want option A or option B? Under damped or critically damped. Okay, we don't call them that because it sounds a bit too technical. We've tried to go with layman's terms. So if we go into our Pilot 1 and we go menu, temperature control, TAC, configuration auto, and under the heading control dynamics, you will find two options. Like I said, we've tried to label these to make them easier. We've got option A, which is fast with overshoot, or option B, without overshoot. And that should give the system the basic PID settings so that it doesn't overshoot on heating or cooling, and it just hits your set point as quick as possible. So in the previous webinar we went through sizing of temperature control units for applications. In this one we're going to look at where are my applications used and what is the operational range of my application. So if we think of an R&D lab, we're going to split this between R&D and production. In the R&D lab, they'll have their reactor system and their Huber. And in the production facility, they will also have their Huber and the reactor system. The key differences between both areas: R&D labs need to be more functional. They've got to have a wider range of operation because they might have new projects coming in, old projects getting renewed, or investigating processes on pipelines that have a wider range of temperature control. So in this case, let's say that we're working from minus 40 degrees C to 200 degrees C. In a production facility, they've got SOPs in place, they know the manufacturing protocol. Often you get a reactor and a TCU that is dedicated to one operation. So let's say we're doing a crystallization and we're dropping out, we've got a cool down ramp from 30 degrees C to minus 20 degrees C. And that's the only operation of this device, is literally just cooling the batch to get a precipitate out. Whereas here we could be doing palladium couplings, nitrations, some Grignard chemistry. So we've got to have a wider range on it. How do we tune the PIDs of these two different styles of units? So in the Huber unit, if you were to go menu, temperature control, TAC, auto configuration, you will see that you have the option to do PID tuning fast or preliminary with testing. So these are the two different, if you read into your PID terms, it's kind of the Ziegler-Nicholas is the fast identification method. And then for the with preliminary testing, we've got Cohn and Kuhn as another method, which takes in far more parameters. But let's move back a step and let's look at how do we set up our reactor system for tuning so that we can get the best results out of it. So again, we're actually going to use a mini stat for this in real life, and we've recorded a couple of videos on that which we will show. So if we've got our mini stat and we've got our 1 liter reactor, key factors we need here before we even start. We need to, number one, have bulk media in reactor. So in this case, we have 750 ml of IPA. Number two, we need agitation. So here we're going to use our Radley's overhead motor, and we're going to go at 2,500 RPM. Number three, we need an external PT100 that is inside the media. Four, we need to know type of thermal fluid. And we need to know 5 volume of thermal fluid. So the Huber unit on installation will ask you for 4 and 5. You've got to tell it what thermal fluid you're using, and you've got to tell it how much is in there. The reason it needs this is it needs to know this value for calculating the initial dead zone temperature. So, how does Huber TAC work? It's quite simple. The Huber unit sends out packets of information, or thermal information as I'll call it. So it sends out thermal packages. So it gives it a blast of heat or a blast of cooling, and it looks at the feedback times. In this case here, so we've got a feedback loop. It's looking at how quickly the internal PT100 and the external PT100 see a temperature change. So we have TI in here, we've got TE here. Sometimes on the Unistat Ranger family we also have a TR, so you can look at your return temperature. So it looks for the Huber unit itself, sends that packet of thermal energy to the application, how long it takes to get that energy from the jacket through the wall of the application, through the bulk media, and to get a feedback signal on the external PT100. It's key that we tell it the correct thermal fluid here, so it knows the specific heat capacity and the volume of this fluid, so it can do its own little calculations and work out my response time from my dead zone is this. We also see that from the TI, and in the case where we've got a return sensor, we can use that data to build up our PID tuning. What the unit then does is it then does a heat up or a cool down. So in this case, the unit will, once it's gauged its dead zone time, so sending these little packets of information around, it will then look at its heat up. So we'll say heat up in this case. And it's looking at the time it takes to heat up to get to roughly the set point. But it will also look at, am I getting an overshoot or an undershoot? Sometimes the machine will tell you your results are nonsense. This does not make sense. So a key factor, which I should have mentioned at the start, was factor number 6, a stable temperature. So with a stable starting temperature, we often tell people to run the machine for about half an hour beforehand when doing a kind of a fast identification loop tuning. So here you'll see we've also got a time lapse of a fast identification and the kind of messages you'll see popping up on the screen while it's doing its temperature control. You just leave it run. It'll tell you when it's finished. And if it cannot complete, it will also tell you that it cannot complete. So where would we use this kind of fast tuning? I would use fast tuning in production, because the system is doing one function. It's cooling down from 30 degrees to -20. What would I set my stable temperature at? In this case, I would set my stable temperature at 0 degrees C, and when asked to input new temperature, which has to be a greater than 10 degree difference, I would simply put in -10 degrees C as my new temperature. The reason I put in -10 rather than -20 is most units have more cooling power between 0 and -10 than they do at -20. And this, in theory, will give you the ideal scenario for a fast tuning. But please remember, you do have to, as in point 1, have your bulk media in your reactor. If you're trying to PID a process tune with air in the reactor, obviously you'll get dud results because the jacket won't transfer the temperature via the air to the PT100. So, if you're doing a one function reactor, fast tuning is fine for either heating up or cooling down. And then you can also adjust the control dynamics to tighten that control once you've done your PID tune. So if you think back, we mentioned fast with overshoot or no overshoot. Slightly more complicated is the R&D setup, where you may want to work across a wide temperature band. I will guarantee you now, if you were to set your stable temperature at 100 degrees C here, and let the machine try scope out its PIDs from the values of -40 to 200 degrees C, it will not do it. It's too wide a range. What we need to do here is be a bit clever about this and look at where does my machine have its maximum cooling power and its minimum cooling power. Where have I got my heating, which normally is electrical, so we've got that available across the board. So when you're setting up a multifunction chemistry application and you want to do a wide tuning on it, in this case we're going to do tuning with prelim testing, and this would fall under the cone and coon kind of testing. This graph does look a bit overbearing, but it's not to worry about. So in the fast tuning, we're essentially adjusting our P value, how quickly we got places, and we could get that with our dead zone. So our initial sending those little packets of thermal information around, seeing when they pinged each temperature sensor and how quickly the heat transferred into the reaction system versus how quickly we could get there. In the cone and coon, or the with prelim testing, we're going to also adjust our I and D values using our tuning setup. So it's a bit more of a, we look at measured and maximum rates of change for this complete system. But how do we actually do that on a Huber unit? So we have done a little time lapse here as well, where we can show with prelim testing. And what you'll see is you start with your stable temperature and the machine will then scope out between your minimum and maximum set points, which you've done in the top left hand corner of your pilot 1. So we've got a slightly different setup here. So 1, we need our bulk media again. Always test with media in the reaction system. 2, we need agitation. 3, we need external probe. In media. Now 4 is slightly different on this one. 4, we're going to adjust our min temp. 5, we'll adjust our max temp. And then of course we need to do as before, type of HTF. Seven is volume of HTF, and then 8 is a stable temperature to start with. So we've got our 8 points where we've talked about we need to adjust our min and maximum temperature. Why do we do that? As stated, if we were to actually try PID tune from -40 to 200 degrees C, I won't lie, our unit won't like it because that's a very vast data range and the machine has a varying range of cooling powers across that range. So if we're to draw a graph here, with minus 40 being our starting point, 0 degrees C and 200 degrees C, where we need to look at is, okay, so our heating, we've got an electrical heating system, so we know that we will deliver X kilowatts continually across all temperatures. So we can kind of remove the top half. For tuning with preliminary testing, the ideal scenario is plus or minus 30 degrees C. So in this case of our R&D reactor, I would set our T-min at minus 30 degrees C and our T-max at 30 degrees C. We've done a video on how you can set your minimum and maximum temperatures. We'll put a quick reminder up here in an in-screen shot. So our starting temperature, we will go at 0 degrees C. Obviously, make sure you're not using water as your reactant contents if you're at 0 degrees C, because you will get ice. So our starting temperature, before we start our preliminary testing, I would say allow 30 minutes to 1 hour at 0 degrees C, so that we've got a stable starting temperature. We know our external PT100 probe is stable, the agitation is stable, we're not generating heat from the system. And what you'll find is, because we've now curtailed a T-max of plus 30, a T-min of minus 30 in our system settings, the unit will do its initial dead zone finding. So like in the fast tuning, it will send little packets of thermal information and try ping the different sensors. It then calculates using the heat capacity of the thermal fluid and also the volume, a kind of a response time to get feedback. And then it looks up at, then it will start looking at heating up and cooling down, how fast it can do it, and will it overshoot. So what you often see, as you'll see in the time lapse we'll show just here of tuning with preliminary testing, the unit will often apply heat, it will then change its set, it'll hold, it will change its set point, drop down, it'll go up, and it will just scope its way out through the system. Again, you will get a message if the system isn't happy and cannot find optimum conditions. If that does happen, just try throttling back your T-min and T-max, or adjusting them slightly, say minus 20 plus 40, and the unit will scope it out. This kind of zone between 30 and minus 30 we find very useful on large unistats, say 900 series, which typically work at minus 80. This often gives better results across a wider range of temperatures than just doing it at minus 50 to minus 80 and minus 50 to minus 20 degrees C, because we're getting the maximum cooling power out of the unit here. So tuning with preliminary testing can take a while, I won't lie. Whereas fast tuning can be done in about half an hour. This might take an hour or two because it's scoping between the different temperatures to give the best results. And when it has completed that, like I said, the machine will tell you. A question we're often asked is, how many PIDs can I store in the system? I won't lie, the answer is 1, because you've got to tune to an application that you're running. The last thing we want someone to do is to apply incorrect PID values by selecting a second option, third option, or fourth option in the menu, and then they would lose a batch or something would be outside conformity. How do I get around that? So Hubers are often used as a utility machine, and I'm aware of many cases where, let's take for example, a 510W is used on a 20 litre glass reactor, 100-litre steel reactor, and a 200-litre glass-lined stainless steel. They will all have different TAC configurations. How we get around this is, if you insert a USB stick into the top of your Pilot 1, you can then go Menu, System, System Settings, and you can actually upload the global system settings onto that USB stick. And you can then name it. You can save the file as, well, what most people do is they pick the reactor name and manufacturer, or they might put if they've got an asset label on the reactor, they will save the asset tag number and the Huber unit that it's been tuned with. Save it onto a USB stick, and then you can keep it safe. Some customers then label those USB sticks so they know this is the 20-litre settings. Some customers save them all on one USB stick. But it's quite simple, is pop it in the top, save the settings. So when you swap your reactor system out to an alternative reactor, you can just upload your settings by, again, insert your USB stick, system settings, and in this case go load from USB stick, and then we can pick the reactor system that we're looking for. So what I've actually discussed here is kind of application testing where we're using a process probe. Why have I done that? It's a bit trickier, I'll be honest, because we've got more variables. You do have an option of doing testing and tuning with just the internal temperature probe, and I won't lie, that will complete really quickly and it'll give you good results. But if you want the best results, doing a process tune will give you far better control on your system. We can often improve response times, temperature, stabilities, which will lead to further improvements in your product conformity, sometimes your yield of precipitation, across the range in the chemistry labs. But I hope this video has been helpful. If you're still a bit wary about it, just give us a bell. We'll happily come either visit you on site, if we're allowed with current COVID times, or we can do a Skype call and we can help you tune your system. In addition to this, if we're doing it remotely, we can use our Pilot 1 service software to see what your system's been doing, and we can analyze it remotely and give you some suggestions. But don't be afraid of contacting your local Huber point of contact globally, for Huber USA, Huber India, Huber China, Huber Italia, even the Huber Germany guys. We're all happy to help. You can contact me directly via either my LinkedIn or my email, or just give me a phone call. All of our contact details are on the website. Thank you.